The middle stage of this crash course is I'm going to go through the chapters that are assigned, really all the chapters in the book, chapters 1 through 9. I'm going to go through the rules, the fundamental rules that our chapter are based on, and then we're going to look at some examples that are relevant to each chapter. Now, Chapter 1 is all about problem solving, and Chapter 1 doesn't really have any rules regarding it. Basically, it's, the kinds of questions you're going to get on the exam that are relevant to Chapter 1, which is about problem solving strategies, is you're just going to get, questions that you can really figure out using common sense deductive techniques. Things like trial and error, with drawing pictures and doing things like that. I mean, let's take a look at a couple of the examples from Chapter 1, which kind of illustrate what we're looking for. Here's one type of example that you might see. Let me put that over here. Okay, there we go. A large cube is made up of 3 by 3 cubes. 3 by 3 cubes. Find the total number of 1 by 1 cubes in this large cube. Now, you may be able to figure that out anyway, just off the top of your head, but because a cube, which is 3 by 3 by 3, well, I mean, really the best way to figure that out is a cube. The general way to figure out the volume of a cube is length times the width times the height. Now, a cube is the same in every direction, so it's 3 times 3 times 3. So if you draw 27 of them, that would be, well, it would be 27, because 3 times 3 times 3 is 27. So that's a fairly obvious one. What if it were squares? Cubes are something that you have trouble drawing. But for example, if it's 3 squares by if there are 3 squares by 3 squares, something like this, then, and you made, again, these aren't going to be exact squares, but hopefully they'll be fairly close. If you have something like this, and again, this is not a very good drawing because they're kind of lopsided, but let's assume that they were all equal. Now, if you drew something like this, you would see right away that it takes 9 small squares to do a 3 by 3, because this is two-dimensional. Two-dimensional is you square the amount. If you have 3 on this side, 3 on that side, the total is 9. Let's take a look at another interesting little example that you might see. Something that's really a little bit more about problem solving and analysis more than anything else. Let's take a look at this question here. Assume that you're using toothpicks to build squares. How many toothpicks would it take to make 3 squares side by side so that each square shares 1 toothpick with the hexagon? Well, that should be square. I'm sorry, that's a mistake that I made. So make that the square immediately to its left. Okay. Now, so what you can do is just take out your pen and draw. 3 squares side by side. If you drew 1 square, and it has to be side by side with 1, and assume that each line segment is a toothpick. You can draw this freehand, relatively easy as well. If you have 3 squares side by side, how many, and each side was a toothpick, how many sides are there essentially? Well, in this kind of scenario, you can really just kind of count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it seems like there's 10, which also makes sense because there will be 3 squares. 3 times 4 is 12, and then there are 2 that are being shared. So either way, the answer would be 12. I'm sorry, the answer would be 10. The other thing that's relevant to this chapter in terms of just, kind of doing these sorts of tasks by figuring them out is using algebraic expressions, using equations to figure out geometric expressions. Now, earlier in the crash course, we learned about the number of angles that there are in a triangle, or a square, or a quadrilateral. Remember, a triangle was 180 altogether, a quadrilateral is 360 altogether, a pentagon is 540 degrees altogether. So let's say, for example, just for argument's sake, you're given a pentagon. Let me draw a 5-sided figure. Nice little pentagon here. Okay, whoops. Let me draw a pentagon, actually. Okay. Anyway, so this is a pentagon, a five-sided figure. It's not exactly an equal pentagon, but that's okay. And let's say you are told that this angle is, I don't know, 70, and this angle is 100, and this angle is 2x, this angle is 3x, and this angle is x. You know, instead of making it 70, let's make it 80. Okay, anyway. So, or you're told in words, a pentagon has 5 sides, and one side is 2 times the length of a second side, and a third side is 3 times the length of the first side, and the fourth and fifth sides are 80 and 100 each. Well, the one thing they expect you to be able to do in a course like this is be able to understand what the how to set these up in terms of algebraic equations. First thing you have to know is, okay, what's the relationship between them? And you know that all the angles in a pentagon have to equal up to 540. Remember, angles, if there are 3 sides to a polygon, and that's of course a triangle, then all the angles have to equal 180 degrees. If there are 4 sides, then that's a quadrilateral, and they have to equal 360. And for every number of sides you increase, you got to add 180. So this would be 540. If there are 6 sides, which is a hexagon, it would be 720. If there are 7 sides, which is a septagon, it would be 900, etc. Anyway, so getting back to this example, this is a 5-sided figure, so the total number of degrees have to be 540. So you'd set up an equation, add them all up, and they have to equal 540. So you could say one side, that's x, plus the second side, that's 2x, plus the third side, that's 3x, plus the fourth side, that's 80, plus the fifth side, that's 100. The order doesn't matter, equals 540. And then you could solve this like you would any other equation. Combine the like terms, x plus 2x plus 3x is 6x, of course. The numbers, 80 and 100 is 180. Equals 540, and then you have to solve this like you would any other equation. Subtract 180 from each side, and you have 6x equals 360. Divide each side by 6 to isolate the x, and x equals 60. So for example, if they ask you what the sides are, now the x becomes a 60, the 3x becomes 180, and the 2x becomes 120. And of course, if you add them all up, they better equal 540, otherwise you got a problem. Now, the material for all of Chapter 2 was already covered in the previous section, so I don't think we have to really cover for any material for Chapter 2. So I went to the publisher resources and I picked a couple of interesting examples out of the publisher resources, and I think let's go over that. I mean, in addition to going over the homeworks, I think it'll help. The more questions we go over, the easier it will be for you. Okay, so let's take a look at this one. This is an interesting one. I'm sorry for the barely legible text over here. When I pasted it, I couldn't get it small enough to fit in the window. Anyway, BF and AG are parallel to each other. Where's BF? BF, okay, and AG are parallel to each other. And DEF is an isosceles triangle. Where's D? Oh, it doesn't have D over here. I've noticed some mistakes on the publisher material. But anyway, so I think D is over here. And D is an isosceles triangle. I'm sorry, DEF. Okay, so well, yeah, it has to be. So DEF is an isosceles triangle, which means that 2 sides are equal to each other. And honestly, it doesn't say which 2 sides, but okay, we'll see what is necessary. First of all, what shape is ABDEGHA? ABDEGHA. So how many sides is that? Well, it's kind of a weird figure, but 1, 2, 3, 4, 5, 6. So it looks like there are 6 sides. Any 6-sided figure is a hexagon. What is the measure of angle DFG? DFG, that's the one out here, okay. Well, how would we figure that out? Some of the rules that we discussed, what an angle is to look at angles that are supplementary. Now I'm going to assume at this point that when it said DEF is an isosceles triangle, that these two were the sides that are equal. Those certainly what it looks like, which means that the base angles of an isosceles triangle are also equal. That is true in general, that when you have an isosceles triangle, two triangles, a triangle with with two sides that are equal, the base angles are also equal. Now if this is 74, F and E have to equal up to, combined, have to equal up to 180. Let's use a simple algebraic equation. We'll call this x and that x. So 2x, in other words this side and this side, plus 74 have to equal 180. So subtract 74 from each side, and 2x equals 106, which means x equals 53. Now, so if this is 53, and this is 53, then this, looks like 153 over there. Okay, so this is 53. So this angle, which is the one that they're looking for, DFG, has to equal up to 180. It's supplementary because it's on the same line as this one. So 180 minus 53 is 127. So that should be 127. What's the measure of BAH? Well, that's pretty easy. BAH, oh no, I'm sorry, this is not a triangle. It looked like a triangle, but it's not. So we have to figure out what BAH is. Well, this is not so easy because remember, if this were a triangle, it would be easy. Just take 102 and 69 and subtract the result from 180. But this is actually ABCH is a quadrilateral. So I'm just going to fill in all the angles that I can do, and hopefully that will, in the end, get us to where we need to get. Now, this angle. Well, this angle is supplementary with the 74. So it's 180 minus 74, which is 106. So this is 106. Now this angle also has to be 74, because this is a vertical angle with this, so that has to be 74. I'm sorry, let me write that a little bit more clearly. Okay. Now this angle, well, we don't know what this is. Well, this we know what it is, because this has to be supplementary with 102. So it's 180 minus 102, which is 78. Okay. Now, this is 74 and this is 78, so this angle has to be 180 minus these two. 180 minus, well, 74 and 78 is 152. So 180 minus 152 is 28. So this angle has to be 28. Because this angle has to be 28 and it's supplementary with this one over here, now you see I think we're getting closer and closer. So this has to be 180 minus 28, which is 152. So this has to be 152. Now we've got three angles in this quadrilateral. An angle here, an angle here, an angle here, an angle here. So I'll take the total for a quadrilateral, which has to be 360. And I'll subtract all the others. Subtract 69. Subtract 152, and subtract 102, and what we have left over, it looks like, is 37. Okay, so we've figured out BAH, again, just by filling in all the angles we could. If we're curious about other angles, by the way, remember this was 78, which has to be supplementary with this, so where the h's would have to be 180 minus 78, which is 102. If we wanted to figure out what G is, well, G HDF is a quadrilateral, so it would be 360 minus that 127 that's down there by the F, and then minus 106, which is this angle, and then minus 102, which is that angle, and we got 25, so this is actually a 25-degree angle. And this, of course, has to be 78, because it's supplementary with this, or because it's supplementary with this, or because it's a vertical angle with this. Anything else that we can fill in? Sure. I mean, let's see, is there anything else? Well, okay. This is parallel to this, which means that this angle and this angle are alternate interiors. So this is 74, and that also has to be 74. And this is 74, and that's 78. So that actually has to be 28. There's actually two different reasons why we could figure out this is 28. Number one, because it's an alternate interior with this. This is a parallel line, so this and this are alternate interiors. Plus, if this is 74 and that's 78, that leaves only 28 for this. So we figured out all of the angles here. Congratulations to us. Okay. How many obtuse interior angles are there? Obtuse means between 90 and 180. How many angles are in there in this figure that are between 90 and 180? 1, 2, 3, 4. So I see 4 obtuse angles here. And name them, well, this is DFG. This is FDH, or FDA, makes no difference. This is GHD. And this one is HCB. Just put the point that they're at is the middle one, and the other two are the segments that form the angle. List one set of vertices that form a pentagon. Are there any 5-sided figures here? Well, sure. I mean, there are so many crisscrossing ones we can figure out one that has 5 sides. Let's see, 1, 2, 3, 4. Well, anyway, we'd have to figure out one set of lines. It'll take a little trial and error to figure out what would give you a pentagon. How about this? 1, 2, 3, 4, 5. Yeah, okay. So G, H, D, B, A. That, let me draw this out. I think this would be a pentagon if we did this, 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 and this. Yeah, that would be a pentagon. There are many others, I'm sure, also, but so this would be a weird-shaped pentagon, but it's still a pentagon. It's got 5 sides: 1, 2, 3, 4, 5, and so the vertices would be G, H, D, B, A. List 2 set of vertices that form scalene triangle. Scalene triangle means a triangle where none of the sides are equal to each other. Let me take these down for a second. Well, there are lots of scalene triangles here. First of all, HDC is a scalene triangle because it's 78, 74, and 28. So this is a scalene triangle. Let me fill this in just to show you which triangle I'm referring to. This triangle is a scalene triangle. What else is a scalene triangle? Well, this looks like a scalene triangle. BHA is a scalene triangle. None of the sides are equal to each other. And this is a scalene triangle. GHA is a scalene triangle as well. And, well, there's a whole bunch of them. They asked for 2 of them. Which angles are congruent? Congruent means equal in terms of angle. There's lots of congruent angle sets. HCD is congruent to this one, which is AGH. These 2 angles are congruent to each other. These 2 angles are congruent. The 53 and the 53. There's lots and lots and lots of sets of congruent angles here. One more quick example, one that actually should be relatively easy, also illustrating the fact that all triangles have to equal a total of 180 degrees. You get a question like this. It might be in word form again. It might say something like a person runs his tractor between 3 different points, and the first one says 10 less than one of them is 10. One side is 10 more than the other, and the other side is 2 less than 10 times the other. Whatever the case may be, you have to kind of establish them in terms of x. If you get a word question, you got to try to give the relationship in terms of what they are. If you establish that you have 3 angles in a triangle, one of them is 2x minus 10, another is 2x, another is x plus 10, the way you'd solve this is simply to add them all up, and they have to all equal 180. So that's 2x, which is this, plus 2x minus 10, plus x plus 10, equals 180. And then add them together. 2x plus x is 5x. Negative 10 plus 10 is 0, so that cancels. So that equals 180. Divide each side by 5, and x equals 36. Now then you go back and plug them in. 2 times x is 72. X plus 10 is 36 plus 10, which is 46. 2x minus 10 is 72 minus 10, which is 62. course, you got to add them up, see if they equal up to 180. Well, 62 and 46 is 108. 108 and 72 is 180. Exactly, so this works. Now, I've looked at Chapter 3 as well, and again, we've covered the entire Chapter 3 in the idea before in the previous classes, in the previous lectures. So I want to go straight to solving some problems regarding Chapter 3. Something that's relevant to the material that was covered in Chapter 3 in terms of areas. Area of a circle, area of a square, areas of all those areas of a quadrilateral, etc. Here we have an interesting problem. A rim is 25 inches in diameter. Certain balls are well, take this out, are 25 inches in circumference. Is it possible for two such balls to fit in one rim at the same time? Interesting question. Now, to do that, you kind of have to figure out you kind of have to draw it. Let's draw it and see if this works. Let's see a 25-inch rim. Now, a 25-inch rim in diameter means that, let's say this is the middle. Let's say this is the center. And you would make any line that goes through the center, and this is 25 inches long. So the question is, if you have these two little balls, how wide are they? How big are they? Now, the only thing we know about them is that they're 25 inches in circumference. Now, what's the ratio between the circumference of a circle? The circumference of a circle is 2 pi r. Or, in our case, I'm just going to say pi times the diameter since we're dealing in diameters. So what we know here is that we know that they're 25 inches in circumference, but we don't know the diameter. Diameter is going to be very important to see whether we can stuff these balls in here. So the circumference is pi, we'll round it off to 3.14, times the diameter, which we'll call x since we don't know what it is. To isolate x, we can divide each side by 3.14 like we would in any other equation to figure out the diameter. And 25 divided by 3.14 gives you 7.96. So x is 7.96. So now we'd have to envision, do two circles that have a diameter of 7.96, will they fit into this rim? And I think it's fairly obvious that it will, because the idea is if they're 7.96, that's the entire diameter. Each side of this 25 from the middle, in other words, if you put it in the middle, there'd be 12.5 on this side, and there'd be 12.5 on that side. Now, these two balls are going to be 7.96 each. They can each fit within here. You know, the one 7.96 ball is going to be something like this, and another 7.96 ball is going to be something like that, and they could each fit in. In fact, you might even be able to have a third and a fourth one. You probably wouldn't. You'd definitely be able to have a third and a fourth one. The only question is how many would you be able to fit? Maybe you'd even be able to fit 5 of them. But a question like this, you know, you just kind of draw it and figure it out. There's maybe not an ironclad way to make the determination without actually drawing it. Okay, let's try something like this. And I apologize for my sloppy writing once again. But we're given that AF is perpendicular to AB. So this is a right angle, okay. And this is a right angle, of course. ABCD is a parallelogram, which will be important. And AF is 9. And we're also supplied by some dimensions on the chart. AB is 6, DE is 2, FE is 10, and we need to find the total area. Okay, now the total area, there's two shapes over here. There's a quadrilateral or parallelogram here, and there is a triangle here. So the only way to really do this is to separate them, figure out the area of the parallelogram, and then, actually this is not even a parallelogram, this is a rectangle. I mean, it's a parallelogram, but it's a rectangle is a type of parallelogram. A parallelogram means a rectangle with a rectangle means a parallelogram with a right angle. Alright, so we've got, and then of course the area of the triangle, which is base times height divided by 2. So we've got this side. We do not have the height of the parallelogram. We do have the height of this. Now, so what about the triangle? This is a right triangle. That's good news. That means we can use the Pythagorean theorem. We know what this is. Do we know what this side is? The answer is yes, because in a parallelogram, opposite sides are equal. So if this is 6, then this also has to be 6, which means the height of the rectangle over here is 8 altogether. 6 plus 2 is 8. So this entire thing is 8, and this is 10. So if we want to figure out CF, which will definitely help us, we need to use the Pythagorean Theorem. And the Pythagorean Theorem is a squared plus b squared equals c squared. In this case, let's call this side a squared, so we'll just call it x because we don't know what it is. X squared plus b squared, this side is 6 plus 2 is 8, equals 10 squared. And this gives us, well, x squared plus 64 equals 100. Subtract 64 from each side, and we have x squared equals 36. Take the square root of each side, and you have x equals 6. Okay, so we've gotten that using the Pythagorean theorem that this is 6. Now we know that this whole thing, AF, is 9 altogether. So if this is 6, that leaves 3 left here. So now we've got all the dimensions we could possibly need. Let's do the area of the circle of the triangle first, and then we'll do the area of the rectangle. So the area of a triangle is the base times the height divided by 2. This is a right triangle, so it's very simple. The height is 8, that's this, and the base is 6. So it's 8 times 6, which is 48, divided by 2, which is 24. Now, in a different color, let us do the rectangle, whereas in the rectangle, the area is simply the base times the height, or the length times the width, same thing. In this case, that's 6 times 3, it looks like. 3 over here, 6 over here. 3 times 6, which is 18. If we add them together, the 24 and 18, so we get 42. So the total area of this shape is 42. Okay, now this kind of a question is a question that you're going to see a lot as well. Important to understand how to do a question like this, because it can seem a bit intimidating at first, but the truth is it's not really that difficult. You give a figure like this, and you're asked to find the area of the shaded region. Now, usually what you're going to need to do whenever you're asked to find the area of a shaded region is to find the area of the larger area and then subtract the area that's not shaded. So here we've got two circles, one in the other. This area, this is the midpoint of the big circle. That's why it says M over here. You're given that. And you're given this is 6. So the only way to do this is to find the area of the big circle, and then find the area of the little circle, and subtract one from the other. Subtract the little circle from the big circle, and you have what's left to be shaded in orange. Alright, let's try the area of the big circle. Area of a circle is always pi times the radius squared. Now the radius of the big circle is 6. Because it tells you that's the midpoint. So, and 6 squared is 36. So the area of the big circle is 6 times 6, which is 36 times pi. Now we could multiply it out, estimate it to 3.14, but you don't have to do that. You can leave it in terms of pi. The area of the small circle, on the other hand, well, what's the radius of the small circle? Well, the entire diameter of the small circle is 6, which means the radius has to be 3. So the area of the small circle is also pi r squared, and r is 3. 3 squared is 9, so it's 9 pi. So what's the area of the shaded region? Take the 36, subtract the 9, and your answer is 27 pi. You can leave it in terms of pi. If they ask for you to get the number, just multiply 27 times 3.14. This is true in general. Whenever you get shaded region, very often you're going to have to figure out a bigger region and then subtract the smaller one. Finally, one more question for this section. This is volume. Now, we covered volume in the previous section, but remember, in terms of volume, a cube or any kind of a box, you just measure the length times the width times the height. In a cube, they all happen to be the same, so you just multiply it 3 times, multiply it by itself. Basically, it's any edge to the third power. But a rectangular solid like a box, length times width times depth, 3 dimensions. For a can, which is the one over here, which is a cylinder, it's pi r squared times h, because pi r squared is the bottom of the can or the top of the can, and then the h is the depth of the can. For a cone, it's 1/3 pi r squared h. Let me write them down over here. For a volume formulas. For a cube, which is a box, that's exactly equal on any side, it's any side to the third power, because all the sides are the same. For a rectangular box, it's the length times the width times the height. In other words, all 3 dimensions multiplied by each other. For a cylinder, like a can, it's pi r squared, which is the circular bottom or the circular top, times the height. For a cone, it actually is 1/3 times pi r squared h. Just happens to be that a cone, if you take the cylinder and you cut it and you shave it to the point where it's an ice cream cone, where it ends at one point, and the other side it's the same, it'll decrease its volume by 2/3. That's just the way it works. And a sphere, which is a ball, again, it just happens to be 4/3 pi r to the third power. And this is to the third power instead of h because a sphere has no height. A sphere is the same in every direction. Now, what's a can? A can is a cylinder, so we're going to use this formula. So for the volume in our example, let's use a different color. Volume over here is, for a cylinder, is pi r squared times the height. So our volume is pi times the radius. It tells you the radius is 4. 4 squared times the height, which is 10. So your volume is 4 squared is 16. 16 times 10 is 160. So your answer is going to be 160 pi. You could multiply it out, but again, this question specifically tells you that your answer could be left in terms of pi, so your answer is 160 pi. Our next chapter is about triangle congruence and proofs. Now, a congruent triangle, or a congruent quadrilateral, congruent anything pretty much, means two shapes that are exactly the same as each other. One fits over the other. Now, the two triangles that you see in front of you are congruent to each other. And the reason why I know that is because one is just a direct copy of another. If we copied one, it would fit exactly on top of the other. Well, unfortunately, this blacks out when you try to show it. But anyway, I know that these two triangles are congruent because they're direct copies of each other. So anyway, how do we know whether triangles are congruent to each other? There could be triangles that are separate like that, or they could be part of one big, larger figure. Now, in order for for triangles to be congruent to each other, all the sides have to be equal to each other. This side is equal to this side is equal to this side, and this side is equal to this side, and all the angles have to be equal to each other. This angle to this angle to that angle, and that angle to that angle. Okay. Question is, how do you prove that? How do you establish that? You don't have to prove all 6 things. If you did, it would make things a lot harder. There are 3 ways that you can establish that triangles are congruent to each other. Number 1 is if you just prove that all the sides are equal to each other. This is equal to that, this is equal to that, and the third one is equal to the third one. This means that the two triangles are congruent. It is completely impossible to draw two triangles that are the same sizes of all the sides, and the angles are different. So inherently, that means that the triangles are congruent. This is what I will call SSS is congruent. This is the symbol for congruence, is congruent to SSS. Okay, that's the first one. That's the first possibility. If all the sides are equal to each other. What if all the sides are not equal to each other? Or I should say, you can't prove right away that all sides are equal to each other. There are some other possibilities. The first possibility is that you have 2 sides and the angle in between them. So for example, if this is equal to this, and this is equal to this, and this angle is equal to this angle, the 2 triangles have to be congruent. There is no way to draw a side and then the same angle and the side. And if you think about it, the reason is because even if you took away this side over here, once you drew this side, this angle, and this side, the only way to complete the triangle would be to draw the third side over here. This method we will refer to as SAS is congruent to SAS. The third possibility, and let me erase these congruency marks. The third way is if you have two angles and any side. And the reason is because if you have two angles, by definition, you have the third angle. Now, so if this, for example, is equal to this, and this is equal to this, well, by definition, the third side has to be equal to each other. If the third side, because they have to equal up to 180, so if this and this are combined or the same as this and this, they're each going to have the same amount left to get to 180 for the third side. But the thing is, this doesn't mean necessarily, just because all three angles are the same doesn't inherently mean they're congruent. They could also be what we also discussed as similar, which just means they're in proportion. Doesn't mean they have to be the same side. But if they are in proportion and you have at least one side that's congruent, for example, this side is congruent to this side, plus the angle, that is enough to get you congruency. So if you have this side is equal to that side and you have two angles, I am going to call this AAS is congruent to AAS. Two angles and one side. There's also a fourth that, like when I was taught, I learned the fourth way is SAS is congruent to SAS, which means, ASA. ASA is congruent to ASA, but again, that's really the same thing. 3 and 4 are really the same thing. Any two angles and a side are going to get you there, going to get you to congruency. So the next thing we have is the issue of a geometric proof. How are you going to prove that? Now, of course, congruency is very important in terms of numbers, because we know if these two triangles are congruent, then their corresponding sides and angles have to be equal to each other. We know if this is 50 degrees, then this has to be 50 degrees. We know if this is 10 feet long, then that has to be 10 feet. If this is 15 feet, then that has to be 15 feet. Whatever the corresponding parts have to be equal. That brings us to the issue of corresponding parts, which let me clear the board over here. Well, actually, let me just clear the triangles away and get a new set of fresh triangles. Okay, here are a fresh set of congruent triangles. Now let's say we manage to prove these triangles are congruent by AAS. We proved somehow that this was congruent to this, and we proved that this was congruent to this, and we proved that this side was congruent to that side, or equal to that side. So now the triangles have been proven to be congruent, because you've got two angles and a side, which is good enough. That was method number 3. Okay. That also inherently means, once they're congruent, then all the other congruent rules work too. So this would have to be equal to this. This side would have to be equal to this side, and this side, would have to be equal. That is what is called the corresponding parts rule. Corresponding parts, if we set it in long term, would be that corresponding parts of congruent triangles are equal, or corresponding parts of congruent triangles are congruent. For our purposes, they mean the same thing. Once you have two triangles are congruent, all the rest work inherently. When you're establishing a proof, what I always like to do is to set up a chart with statements and reasons. Let me insert a little table over here. Okay. Now, what I'm going to do is I'm going to put statements on. A proof works with statements on one side and reasons on the other. Let me expand this, but make it so that you're able to see the whole thing. I'll have to zoom in a little bit. This is what my chart would look like. And the reasons, of course, you just put in the mathematical rules. The way a proof works is that you have to prove elements one at a time until you have finally proven that whatever you're trying to prove is correct. Okay, let's take an example and we'll discuss how to prove it. I've got a couple of proofs that we'll do now, and then a couple of more proofs when we go over the homework. Okay, so we've got an example over here. ABC is an isosceles triangle with AB equal to AC, and angle A is equal to 60. Prove that ABC is an equilateral triangle, which means all three angles are the same. All three angles have to be 60 degrees in an equilateral triangle because they have to equal up to 180 altogether. Well, okay, so the first thing, we establish what we've already proven. Angle A is equal 60 degrees. Okay, and the reason for that is we just write given. And number two, we'll write AB equals AC. I mean, you could use the congruent sign, but I don't have the congruent sign over here. So I'll just write AB equals AC, and that's given as well. Okay. Now, I'm thinking about how we would prove this. Sometimes you got to look at it a little bit and just think about how you're going to go about proving it. If you're not sure how to prove something, just prove what you can prove. Prove each element about what the relationships are, and eventually you'll figure it out. Now, looking at this over here, you know that the bases of an isosceles triangle are equal. Now, the bases of these two are not here. It's not, usually the bases might be here and here, but here the equal sides are A and C. A and B, excuse me. I just realized this is actually not an isosceles triangle. This is actually an equilateral triangle, but all right. So isosceles. Okay, anyway, the point is that this is equal to this. That means the two base angles of these sides are here and here. So what I'm going to say next is angle B is equal to angle C. And the reason for that is we can describe it. We don't have to get it mathematically precise. We can say the base angles of an isosceles triangle are equal, and they are the base angles of an isosceles triangle. Okay. Next, so now that we've got this and this are equal, we know that they have to equal 120 altogether, right? Because this is 60. So I'll say angle B plus angle C must equal 120 degrees. And the reason is that all three angles in a triangle must equal 180, and 60 degrees are allocated to angle A. Okay. So now, because B and C are equal and they have to equal 120, I'll say angle B and angle C must each equal 60. Whoops. Put that as the statement over here. Okay, because angle B and angle C are equal and must add to 120, add up to 120. That's fairly obvious. And I'll say that angle A equals angle B equals angle C, and I'll say the way we know that is because all three equal 60 degrees. And now I'm finally ready to prove my answer. I'll say triangle ABC is an equilateral triangle, and then I'll say because triangles whose angles are all equal to each other are equilateral triangles. Okay. And again, I haven't, been so precise in terms of my wording, but that's okay. That works. As long as I can describe it in English, why these things work, then that should be all right. Let's try one more proof. statements over here and reasons over here. In figure ACDF is a parallelogram, and AD and BE bisect each other. AD and BE bisect each other. Okay? Prove that BC is equal to FE. I think this is one of the homeworks. Never mind. So let's cancel this. Okay, I'm trying a different one because I just realized that was one of the homeworks. Let's try a different one over here. Okay, angle V is the vertex angle of isosceles triangle RVT. That means that if this is the vertex angle, that means T equals R. That's what, and RV equals RT. Prove that if VS is the median to RT, which means the median bisects R and T, then VS, this, bisects RVT. Let's put this up over here so that we can be able to draw on it. So let's look at the rules. I'm having a little bit of an issue trying to figure out where to put everything, but we'll figure it out. Okay, V is the vertex angle of an isosceles triangle RVT. So when we have RVT, V is the vertex angle, which means that this angle is equal to this angle. Now we'll have to state that in our proof. It doesn't inherently come that way. Prove that if VS is the median to RT, so we're going to make that assumption. We're going to assume that VS is median of RT, then VS bisects RVT, which means that that's going to essentially mean that this angle would equal that angle, because if bisecting means it splits it into two. So let us go ahead and see how we would go about proving that. So the first thing I'd like to put in over here is that, okay, what are we given? We're given that V is the vertex angle of isosceles RVT. So let's just, start by saying angle V is the vertex angle of isosceles triangle RVT, because that's given. And I will say that R and T, so that means RV is equal to VT, because in an isosceles triangle, the two sides corresponding to the equal angles are equal. And by the same token, we'll say angle R is equal to angle T for the same reason. Again, because in an isosceles triangle, the two non-vertex angles are equal. Okay. Now we've already established that, and we know we're going to try to prove that this is equal to this. Now, it seems to me right away that the way we're going to accomplish this, by getting this angle and this angle, is by proving these two triangles congruent. We already have this angle, and we have this angle. We also have this side and that side. We've got RV and RT. We've got angle R and angle T. We could also get VS, because VS is equal to itself, and it's part of both triangles, but that wouldn't help us. That wouldn't work, because then we'd have a side, an angle over here, and another side. That's not good enough. In order to prove congruence, the two angles that you're using have to be, the two sides that you're using, the angle has to be in between them. You have to get SAS. So what we are going to need is either the third side or another angle. Now, I don't see any particular way to get this angle and that angle, or is there? Well, if it was established that VS was perpendicular to RT, well then of course these angles would both be right angles and we'd be able to get them, but it doesn't say that. It does say that VS is the median to RT. So that means that RS is equal to to ST. So that will help us. RS is equal to ST because a median, which means bisects a line segment. Okay. So now we've got RV and VT. We've got RS and ST. And we've got angle R and angle T. We set all those up. So based on that, we can say triangle RVS is congruent. I'll use the equal symbol to VST because we've got SAS. We've got this side, this angle, this side is equal to this side, this angle, this side. So I'm going to say SAS is equal to SAS. We could have also gotten SSS and SSS because I'm using VS, but either way is fine. Now we can get this angle and this angle. We can get RVS. Angle RVS is equal to angle SVT because of corresponding parts. The sides are of congruent triangles are equal. Now we have what we're trying to prove. VS bisects angle RVT because an angle bisector forms two equal angles. And as we know, these two angles, which are bisected by this line, we already proved them equal in this step. So now we've proven our step. Congratulations. Okay, Chapter 5 is all about parallel lines, rules with triangles. A lot of these we've discussed already, but I'll go over them one by one. And these, let's assume for the sake of this chapter, for the rest of the chapter, these two lines are parallel. So happens they are parallel, but let's assume that they're parallel, and let's discuss the rules that apply. Let's assume you have two parallel lines, and let's assume that you cut them with a line like this that's called a transversal. Now, the first rule is that alternate interior angles are equal. Now, alternate interiors would be, let's say, 1 and 2. Alternate interiors means on the other side of the transversal, other side of the transversal and on the same side of the parallel line. That's why they're interior, but they're alternate. So 1 and 2 are equal. Angle 1 equals angle 2. What about angle 3? Now, angle 3 plus angle 1 equals 180. They're supplementary. The reason why they're supplementary is because, well, there are a couple of reasons. The main reason is because angle 1 equals angle 2, and angle 2 and angle 3 are on the same line, which means angle 2 and angle 3 have to equal 180. So that means also angle 1 has to equal 180. Angle 1 and 3 together have to equal 180. Consecutive angles, for example, let's take a look at number 4. Consecutive angles like this, on the outside, here and here, 1 and 4 have to be equal. Now, of course, the reason why 1 and 4 have to be equal is because 1 and 2 are equal, because of alternate interiors. 2 and 4 are equal because they're vertical angles. Okay. Fairly self-explanatory. The next rule is if both sides, both lines, are perpendicular to the same transversal. Notice we have two lines over here. We don't even know if they're parallel yet, but if they're both perpendicular to the same line, this and this are perpendicular, then by definition, these two lines have to be parallel. And again, this is just a matter of logic, because if they're both perpendicular to the same line, then this is 90. Well, then that also has to be 90, and that means alternate interiors are equal. If alternate interiors are equal, I mean, this also happens to be 90, of course, and this has to be 90, but the point is this and this are both 90, which means this and this are equal. And just like if once we know that the lines are parallel, we can get the alternate interiors, opposite way works too. If alternate interiors are equal, that means the lines are parallel. That's the third one. And this, of course, will help us do proofs when it comes to, and figure out numbers when it comes to these sorts of problems. So, for example, if I have something like this, and I told you, for example, that this was 2x, and this is x, let's say I told you this angle was twice as much as this angle, and for example, I told you that this was 50, let's say, you should be able to get everything else relatively easily. Now, the reason is because x and 2x combined have to equal 180. They're on the same side of the transversal. This and this are the same, so this and this have to be equal up to 180. So it would be x plus 2x, which 3x equals 180, which means x is 60, which means this one is 120, which means this has to be 60. Now, this is 50, so that also has to be 50. No, whoops, I'm sorry, that can't be. Let's call this 150. No, well, instead of 50, let's call this 100. That makes more sense. Anyway, so if this is 100, that has to be 100, so that has to be 80, so that has to be 80, so this has to be 80, because it's alternate interiors with this, which means this, all these three, have to be 180 altogether, and 80 plus 60 is 140, so there's 40 left in here. This, of course, well, this is 120, so this has to be 60. All three angles have to add up to 180, which they do. This, of course, has to be 120, because it's vertical with this, and supplementary with this. That's 60. Again, and let's see, what's over here? This has to be 40, because it's vertical with this. This has to be 80 because it's vertical with that, and that has to be 60 because it's vertical with that. So you can use it to make these calculations, and of course you can also use it to do proofs if necessary. A couple of more quick theorems. If we have an angle, a triangle like this, and we call this angle 1, and this angle 2, and this angle 3, and this angle 4, this is the exterior angle theorem, and the exterior angle theorem says angle 4 equals angle 1 plus angle 2. In other words, something that's on the opposite side of a straight line from one of the angles of the triangle has to equal the other two combined. Now again, this is fairly obvious. You don't even really need this theorem, because 4 has to be supplementary with 3. Which means 4 plus 3 have to equal 180 because they're on the same line. Now, 1 and 2 and 3 combined also have to equal 180 because they're inside of a triangle. So just like 4 has to equal, just like 4 has to equal 180 minus 3, 1 and 2 also combined have to equal 180 minus 3. So 1 and 2, of course, have to be the same as 4. One more congruence theorem. Last lesson we discussed the SAS, SSS, and AAS methods of proving congruence. For a right triangle, there's actually one more method of proving congruence. And let me draw a nice little right triangle down here. And this is what is sometimes known as the High Leg Theorem. And let's get another right triangle that is congruent to this. And again, I'll just copy and paste it so I know that we've got two triangles that are congruent. Now, normally, you would need either, this is, of course, an angle, obviously. This has a right angle, and that's a right angle, so they're equal to each other. So if we got the two legs equal to the two legs, this is equal to this, and this is equal to this, well, then we know that they have to be equal. We know that the two triangles have to be congruent because of SAS, side angle side. However, with a right triangle, there's a special rule called the high leg rule. High leg rule. And that is that if you have the hypotenuse and one leg that are equal to each other in a right triangle, that's good enough. Even though normally just one side and two sides and an angle not between them doesn't work, in this case it does. In this case, with a right triangle, you have a right angle, you have the hypotenuse and one of the legs. That works. We've already covered everything that's relevant to Chapter 6, so we're just going to look at some problems. But before we do that, there's one thing that we didn't cover, and that is the law of sines. Now, you may recall, hopefully, from a little bit earlier in this video, We discussed the sine, cosine, and the tangent, and normally those only work with right triangles. If you have a right triangle, the sine of one of the base angles is opposite over hypotenuse, the cosine was adjacent over hypotenuse, and the tangent was opposite over adjacent. Now, that only helps with only right triangles. This, as you can see, is not a right triangle. However, there is still a law of sines that allows you to figure out these sides by proportion. And the proportion essentially says that in a particular side, let's say this is A, and that's B, and that's C, and that is that A is to the sine of A, and when I say A, I mean this side being A, and this side being C, and this side being B, because that's the opposite angles, is B is to the sine of B as C is to the sine of C. So for example, let's say A is 30 degrees. And let's say C is 70 degrees, and so B is 80 degrees. That was what it would have to be in order to equal up to 180. Now let's say that A we know is, let's say 10 units, whatever it is, and we're trying to find out what B and C are. We're trying to find out what these two sides are. Well, first thing we would need to do is get the sines of all three angles in order to establish this. Let's use this as the relationship and use three fractions. Well, the sine of A, let's get the sine of 30 degrees. Now, let's get our calculator here. Let's do 30 degrees and do the sine, which I know is 0.5, but just to make sure. So the sine is 0.5, so I'm going to write 0.5 on the bottom. Now, let's put the side opposite that, which is 10, so we can put that over here. And let's keep filling it out. Let's say angle B. Angle B is a sine of 80. So let's say 80, and let's do the sine of 80, which is 0.98. So we'll put 0.98 over here. And what about the sine of C? The C is 70. So 70, sine of 70 is 0.94. So we'll put a 0.94 over here. Now, in order to figure out what side B is, we would use this proportion. In order to find out what side C is, we'd use that proportion. And we could use them both off this one. So let's start with B. B is 10 over 0.5 equals x over 0.98. Okay, cross multiply. 0.5x equals 10 times 0.98, which is 9.8. Divide by 0.5, and x is going to equal, I believe, 19.6, which I believe is correct. So we're going to put a 19.6 over here, which means that this side B, is 19.6. And when we do this, by the way, I'm just thinking right away, just off the top of my head, it looks like that's going to be 18.8, if I'm not mistaken. Yeah, I mean, you could do the same proportion, but in my head it seemed pretty apparent that this was going to be 18.8, and so this side is actually going to be 18.8. So using the law of sines, we actually figured this out. Okay, let's take a look at some problems that are relevant to this chapter, based on material that we've already covered. All right, let's see an example here. I'll make it a little smaller so that you can see the whole thing. Okay, given the figure below with OS parallel to UR. Okay, OS is parallel to UR. Find the following: the length SR, the length of OS, and the ratio of the perimeter of the smaller circle to the bigger circle. OFS to UFR. I'm sorry, the bigger triangle and the smaller triangle. Anyway, the first thing that's very important to realize is that the two triangles are similar to each other. Why are they similar? Well, first of all, they share angle F. Angle F is an angle in both of them. But also, these two lines are parallel. So if these two lines are parallel, this angle has to be equal to this angle. They're consecutive. Consecutive angles, remember, if there were a angle here, it would be an alternate interior with this, and it would be vertical with this. So consecutive angles are equal, which means that has to be equal to that, and that has to be equal to that. So these are similar triangles, which means they're in proportion. So this side, 3, this 3, FO is 3, and FU is 8. So the ratio of everything is going to be 3 to 8. This is 3, the long side is 8. So what's on this side? Well, let's do a simple proportion. 3 is to 8 as 4 is to x, because we don't know what the long side is. Let's multiply it out. 3 times x is 3x. 8 times 4 is 32. And x is going to be 32 thirds, or we'll call it 10 and 2 thirds, or 10.666. So this whole side is 10.666, which means this area over here is going to be 6.66. And this is going to be the same ratio. 3 is to 8 as, well, as we don't know what the smaller one is, so we'll say x is to 7. So let's multiply it out. 3 times 7 is 21 equals 8x. And so that divide each side by 8, and that gives you 2 5/8, or 2.625. Again, all I did was I divided this by 8 and that by 8. Okay. And then for the perimeter, well, the perimeter is going to be the same ratio by definition. The perimeter also has to have a 3 to 8 ratio. Chapter 7 is the rule about the various rules regarding circles. And so what I'm going to do here is I'm just literally going to, one after another, go through what the theorems are, what all theorems are. I'll say them each in plain English, and then at the end we will hopefully go through some examples. Okay, the first rule is the rule of area of a sector. Now let's assume that this is a circle. Let's assume that this is the center. And let's assume that we've got two lines that go to an arc. Two line segments that go to an arc. Okay, a couple of things. First of all, this angle, because this is a central angle, because this is the center of the circle, this angle is equal to this arc. If this is 70 degrees, then this arc is 70 degrees. Number two, if you want to know what the angle here is, how much of this circle takes up, in other words, this whole area, this whole 70 degrees, this whole orange area, well, then you'd have to figure out the entire area of a circle, and the entire area of a circle is pi r squared. And once you figure that out, you would divide by whatever percentage this takes up. Now, this, of course, of 70 degrees, there's 360 altogether, so you'd have to divide 70 by 360. In order to make this a little easier, let's make it 80. Let's make it 90, just to make it a little easier. If this was 90, and this would be 90 out of 360, so that would be 1 at 4, so this would be 1/4 of the circle. Whatever the entire area of the circle was, you'd get it down to 1/4 of that. That's the second theorem. Third is the inscribed angle rule. The inscribed angle rule says that if you have an angle that goes from one end to another, the angle itself is 1/2 of whatever the arc that it intersects. So if it intersects an arc of 60 degrees, then the angle over here is 30 degrees. Similarly, for the same reason, if you have two angles that inscribe the same endpoints, where's my line? For example, you've got two different angles but they both intercept the same endpoint, like this. These two angles have to be equal, because they're both half of the same arc. Angle 1 and angle 2 have to be equal. Number 3, if two lines are inscribed in a semicircle, then it has to be a right angle. So for example, a semicircle is one that ends in in a diameter. Let's say this is the middle. And then let's say we've got a diameter over here, which goes all the way across the circle. Okay. Now let's say we've got an angle that's inscribed in the semicircle. In other words, an angle that goes here and to here. Well, this by definition has to be a right angle. And the reason why it has to be a right angle is because the arc that it's intercepting is a semicircle. And a semicircle is 180 degrees. This is half the arc, so if the arc is 180, this by definition has to be 90. Next rule is that if you take any chord, and a chord, remember, is any line that goes from one end to another, not a diameter. Let's use a different color. Let's say a chord. Now this is not a diameter. If you're going to draw a line perpendicular to it, any chord, a line perpendicular to any chord has to be a diameter. Which means if I were going to break this in exactly a way that is exactly perpendicular to it, and again, I'm probably not going to draw it that well, but the point is any chord that is the perpendicular bisector of this. The perpendicular bisector of any chord. Remember, perpendicular bisector means two things. Number one, it has to be perpendicular. This has to be a right angle, of course. And it also means that this side has to be equal to this side. If that's true, if it's true, a perpendicular bisector of any chord in the entire circle is going to have to be a diameter. In other words, the only way to do this, the only way to bisect a chord in a way that's perpendicular, is to shoot something straight through the center. The center is going to have to be somewhere in there, which means that this is going to be a diameter. Next, we've got two theorems that are relevant to crisscrossing chords. Notice AEC and BED are both chords. They're not diameters, of course. Now, the first one is, let's say we figure angle 1 and 2. Angle 1 and 2 are the same, of course, because they're vertical angles, and each of them is equal to the average arc that it intersects. So, for example, angle 1 is equal to the arc AB, the average of arc AB and arc CD, which is the same thing as saying arc AB plus arc CD over 2. Because the idea is both of these combined have to sweep out the arc, and these angles are the same. Same thing is true as, of course, with angle 2. Angle 2 also has to equal the same thing. Arc AB plus arc CD over 2. Together, they have to sweep out the arc that's equal to their combined angles. And since the angles are equal, each one is equal to the average. Next issue is regarding the segments. And that is that the products of the two segments are equal to each other. So this segment, segment 1, times this segment, segment 2. Let's get the angles out of there. Let's say this is segment 2, this is segment 1, this is segment 3, this is segment 4. This means that segment 4 times segment 3 is equal to segment 1 times segment 2. So if, let's get rid of this, get rid of the angles over here. So if this, for example, is 10, and this is 4, and this is 5, and we want to know what this is, it's simply a matter of saying this times this equals this times this. So it will be 5 times x equals 10 times 4, which is the same thing, obviously, as 5x equals 40 divided by 5, and x equals 8. So this x would have to equal 8. The next few theorems are all about secants and tangents. Now, secants and tangents are lines that are from or line segments from a point external to the circle and hitting either the side of the circle or going to the middle of the circle. A secant is a line such as this one that starts at an external point and hits the circle in two places. In other words, goes through the circle. A tangent, on the other hand, is a line that starts on the outside of a circle and goes perpendicular to the circle. In other words, kind of grazes the side of the circle. This would be a tangent. Really, the tangent would be between the external point and the point at which it hits the circle. I'm not conveying that with this drawing, but it really only hits the circle in one particular point. And so that would be the tangent. If this is A, and that's B, and that's C. So AB is a tangent, and AC is a secant. The first rule has to do with angles, and this applies whether you're talking about a secant or a tangent, or one secant and one tangent. And this rule is that if you have, let's say, two secants, or one secant and one tangent, or anything to that effect, if you want to know the angle of the two secants, if you want to know this angle, for example, this angle is equal to 1/2 of the difference between this arc and this arc. So if this is A, and that's B, and that's C, and that's D, so, and let's say that's E, so we'll say angle E is equal to 1/2 of the difference between this arc and this arc. So 1/2 of arc CD minus arc AB. So whatever this arc, let's say this is 120 degrees, and this is 40 degrees. So you take 120 minus 40, which is 80, and angle E is 1/2 of that, which is 40 degrees. The same rule, incidentally, applies when you're talking about a tangent and a secant, or two tangents. For example, if I have a line up here, or a point up here, and I have two line segments, one of them that goes here, and one of them that goes here, same rule. If, let's say, this is E, and this is A, and this is B, and this is C, so angle E is equal to 1/2 of the difference between the big arc, arc AC, minus arc AB. In other words, just take the big arc, subtract the small arc, take 1/2 of the difference. So if this is, let's say, 60 degrees, and the big arc over here looks to be a lot, let's say 260 degrees, so 260 minus 60 is, well, it probably wouldn't be that much. Let's change this to 220. So 220 minus 60 is, of course, 160, which means angle E is 1/2 of that, so angle E would be 80 degrees. And the same thing if it's two tangents. If this line were, if we drew another line, and the line was something like this, and we wanted to know the angle of the big angle, we want to know this angle, we'd have to take whatever this arc is, all the way around the circle, or until here, and then subtract this arc, the little one, AB, and take 1/2 of that. In other words, it's the same rule that applies in terms of figuring out this angle, whether you're talking about two secants, two tangents, or one tangent and one secant. The next rule is about the lengths of the segments. If we've got two secants, we got one over here and one over here. And the rule is something similar to what we saw with chords, and that is that the products of the lengths of the segments formed on one secant equals the product of the lengths on the other secant. with respect to the parts inside the circle and with respect to the parts outside the circle. Now I know that doesn't mean anything in a vacuum, so I'll draw the numbers, the letters over here. Let's call this E, and let's call that B, and that D, and that A, and that C. So what this tells us is that this long secant, EA, multiplied by the short one, in other words, EA times EB, is the same as the product of this secant, which is the long one, EC times ED. The segment outside the circle multiplied by the entire secant and is equal to the product of the part outside the circle times the entire secant over here. Again, I know this is a lot of memorization, and that's of course why you need to actually practice these. You need to look at a few examples, and until these things become fairly intuitive, because you just use them over and over again, you'll remember them. You don't actually have to memorize them, you just have to kind of use them a little bit until they kind of get ingrained in you. The next rule is that a radius, or a diameter of a circle, is perpendicular to any tangent of a circle at the point of its tangency. In other words, what that means, again, in English, let's take a line over here and let's make a tangent to the circle. Now remember, there's only two possible tangents for any line. There could be a tangent on this side, one that runs and hits the side of the circle over there. And there could be a tangent on this side that runs to the circle over there. Now we know that those two tangents from a previous section are equal. Now let's say we draw a radius of the circle. Let's draw a point in the middle. This is the center of the circle, let's say. And then let's say we've got radii. Now, of course, a radius can be anywhere, but let's say we draw a radius straight up to the exact point at which the tangent hits the circle. And then we draw another one on this side. The orange lines have to be perpendicular to the maroon lines. This is a right angle over here, and this is a right angle over here. Because, in other words, if you draw a tangent to a circle, and then you draw a radius that hits that point at which it hits the circle, it has to be a right angle. And again, if you draw it, it should become fairly obvious from the naked eye that that's true. Now, we already discussed before the next rule, and that is that all tangents to a circle from the same point are equal to each other. So if this is A, this point is B, this point is C, AB has to equal AC, because it's from the same point to the same circle. And finally, one last rule before we look at some examples. And this is a little bit more complicated. So here is a point outside the circle, and we've got a tangent. It goes to hits the side of the circle, and we've got a secant that goes through here, and we will call these points A, B, C, and D. And the rule is that the tangent is the mean proportional between the segment outside the circle of the secant and the whole thing. So, for example, the mean proportional means when you have two proportions, the thing that's the mean proportional goes on the bottom of one fraction and the top of the other. So segment AB can go over here and over here. And over here goes the outside component of the circle, which is AC, and the other is the entire secant, which is AD. So, for example, if I told you that this is 10 inches long, or whatever, and this is 5 inches long, and I asked you, what is the entire AD? Well, you could use this formula. Now, AC is 5, AB is 10, equals AB 10, and this we don't know, so we'll call it x. That's the entire AD. So 5 times x is 5x. 10 times 10 is 100. Divide each side by 5, and x equals 20. So the entire AD equals 20. And of course, that also means that CD has to equal 15. Because if AD is 20 and AC is 5, CD is the remaining 15. Now, for the examples, there are a bunch of them in the homework, so I go over in the homework section. Here's an example. I'm not going to go through the entire statements and reasons thing like we did earlier, but this is an interesting one. These are all chords of a circle, of course. AE is congruent to EB, so let's mark that. AE is congruent to EB. Prove that AD, this, is congruent to BC. How would we go about doing it? Let's do an abbreviated proof over here. We'll do a little chart here, and we'll do the statements and reasons. Now, of course, you start with, just whenever I see something like this, the thing that I am going to try to worry about, the thing that I'm going to try to figure out is how do we prove the two triangles? Because if we prove the two triangles congruent, we can get BC and AD with corresponding parts. Now, it tells us that AE, whoops, not the angle, the side AE, the segment AE, is congruent to side EB. That's given. Now, how about this angle? We can get these two angles based on vertical angles. So let's say angle AED is congruent to angle BEC. And that's because they are vertical angles. I'll just write it. Okay, vertical angles. Now, is there any other sides that we can get? Well, the answer is yes. We can get ED and EC. Why is that? You may recall that these products, the product of this side and this side, whenever you have two chords that intersect, the products of the lengths of each side of the chords have to equal each other. Means AE times EC have to equal BD times ED. That was one of the rules. Now, if AE are equal, AE and BE are equal, well then these two have to be equal also. Because if the product of this times this has to be equal to the product of this times this, and these two are equal, well then by definition these two also have to be equal. Now I could write it all out rather than explaining it, but in the interest of conserving time, I'll you see why that is? Again, let's draw this a different color. This segment times this segment have to equal this segment times this segment. That's one of the rules of chords. When chords intersect, the product of each side of the chord have to be equal to each other. Well, if the orange segments are equal to each other, then the only way the product is going to be equal to each other is if the purple segments are equal to each other as well. And because of that, we've got this side, angle side, is congruent to side angle side, so we can get the triangles AED and BEC, and once we do that, then we can get BC and AD via corresponding parts. Now, there are some great problems that I have over here that are probably a little bit too hard. They're harder than any question that you're going to see on the test. But I think, to illustrate some of these rules with regard to circles, I think it would be interesting to look at some of these. Here we have a problem. I'll make it small enough so that you can see it here. Okay, here we have an interesting one. In an archaeological dig, fragments of pottery are uncovered. One piece appears to be part of a plate or other circular flat dish. Use the measurement shown below to find the radius of the original dish to the nearest centimeter. So what I've done to solve it, really the first stage, is to kind of reproduce it on a circle, using this top half. Now obviously this is cut off, so we don't know exactly how far the bottom is, but we do know that this is 8, and the entire length all the way across is 24. So we'll call it 12 on this side and 12 on this side for a total of 24. Now, this all because it tells you that B is the midpoint of PQ. So what I'm going to do to try to figure this out is, well, let's complete this down here. Note, of course, that this is a radius. I'm sorry, this is a diameter. And the reason is because a diameter is a perpendicular bisector of any chord in the circle, which it says right over here it says it's perpendicular, and it says it's a bisector. So it's a perpendicular bisector. So that's actually the radius of the circle, which means that the center of the circle, wherever that happens to be, is going to have to be on this green line. But of course, in order for that to help us, in order to figure out what the radius is, in order to figure out what the diameter is, in order to figure out anything, we got to figure out the length of the green line. Well, here we can use the rule that the product of each side of any two chords in a circle have to equal each other. So this times this has to equal this times this. So we're going to say 8 times this, which is x, times the green line, which we don't know, so we'll call it x, equals 12 times 12, which is 144. Divide each side by 8, and you get x equals 18. So this, the green line over here, together, has to be 18. Now, so that means the entire diameter is what? The entire diameter is 26, 18 plus 8. That's the entire diameter. So if the diameter is 26, that means the radius of this circle is 13. So if we want to know find the radius of the original dish to the nearest centimeter, well, it's 13. It's a whole number. It's 13. If we wanted to know the area of the dish, well, that would simply be 13 squared, which is 169 times pi, because the area of a circle is pi r squared. So here we just kind of used the two rules. We used the one rule that the product of each side of two chords that intersect each other have to be in proportion. The products have to be equal. And we used the rule that if a diameter is a perpendicular bisector of any chord that it intersects. A similarly interesting one, these are all applications, which really make them interesting, because you can see they have real-life applications here. A parcel of land is circular, as shown, with a road running on its straight side. According to the surveyor, the distance from A to B, this line, is 8 miles, and from P to Q is 16 miles, where PQ is perpendicular to AB, Q is the midpoint. What's the radius of the circle? Okay, and how many square miles is the parcel of land, the whole circle? I'm going to draw a different circle to make it a little bit more usable, and that we can put the numbers in. Okay, let's draw AB as a chord. Now, obviously, it shows the road over here, which kind of, makes you not able to see the corner, but the corner of the circle over here. But let's draw it over here to make it somewhere like this, and then we'll say this point is A, this point is B, Q is in the middle over here, okay, O is in the middle of the circle, so we'll make an O somewhere down here, and P somewhere down here. This is really, we're going to use the rules that are kind of the same as the one we already saw, because if we draw this diameter, it goes through the middle, so it's a diameter, and it goes through this point. This has to be a perpendicular it tells us that it's a perpendicular bisector. PQ is perpendicular to AB, and Q is the midpoint of AB, which means that it is a perpendicular bisector, and that tells you that this line, the green line, is a diameter of the circle. Now, what do they tell us? They tell us AB are 8 miles, so we'll say 4 on each side, and PQ is 16 miles from here to here. Now, we don't know what this is. This we'll call x. So we'll use the same formula to figure out what x is. Remember, this times this has to equal this times this, by definition. So let's try it out. 16 times x, which is 16x, equals 4 times 4, which is 16. Divide each side by 16, and we know that x equals 1. So now we know that this x is 1. So what does that tell us about the entire diameter? Well, the entire diameter of the circle is 17, 16 plus 1, which means the radius is half that, which is 8.5. Okay, so that's the radius. So that's the first part of the question. How many square miles are in the whole parcel of land? Well, that's easy. That would be 8.5 squared, because it's pi r squared. And the radius is 8.5. 8.5 squared is, whoops, I'm sorry, 1 second. 8.5 times 8.5 is 72.25 pi. If we wanted to get it to the nearest mile, we could multiply that by 3.14. We could get approximately 226.87 square miles. Here's another great one, a hard one, but a really interesting one. Here we know 3 homes are located as shown. A well has to be placed somewhere in the middle so that it has to be equidistant from all 3. It has to be the same distance from all 3. Now, the only way to get something where all 3 are the same, you have to establish a circle so that all the 3 points are on the radius. Now, if you may not be familiar with locus, if you took the New York State Regents, you covered locus in 10th grade. But the general rule is that if you want all points that are equidistant from a particular point, that you have to draw a circle where all 3 points are on the end of the circle. So we have to draw a circle where all 3 points are on the end of the circle. Now, this is going to be a little hard. It's going to take a little trial and error. Well, anyway, I'm just going to have to actually draw the circle. It's not going to be very precise, and I apologize for that in advance. But let's try to draw a circle where all 3 points are on the circle. Okay, this is the world's worst circle ever. But anyway, it'll do for our purposes. Okay, so anyway, the midpoint is going to be somewhere in the middle over here, obviously. But we're going to have to figure out, what is the radius of this circle? Now, the only information we have over here is that 2 chords are 1.5 miles and 2 miles. And the other thing we know is that this has to be a diameter. The line that goes through the center to C has to be a diameter. The reason for that is another one of the rules that we learned in this chapter, and that is that an arc, I'm going to have to erase this and make a real looking semicircle. It's just driving me nuts. It's not. I'm probably not going to give you a very good semicircle, but at least I can give you something better than that. All right. Well, let's do it in the same color as the original. All right. Anyway, close enough. The point is that this has to be a diameter, because any right angle, which is a 90-degree angle, has to intercept 180 degrees worth of arc. Remember, whatever this is has to be equal to 1/2 of whatever this arc is. Now, if this is 90, then the arc it intercepts has to be 180. 180 is a half a circle, so each side has to be a semicircle. Okay, so this is 2 miles. So all we know so far is that this is a semicircle. This is the diameter, the red line. This is 1.5, this is 2. So, how can we figure out what the diameter is? Well, this looks like a right triangle, right? So let's use the Pythagorean Theorem to figure out what x is. Well, so this is side A, side B, and side C in the Pythagorean Theorem. A squared plus B squared equals C squared. So we've got 2 squared plus 1.5 squared equals x squared. 2 squared is 4. 1.5 squared is 2.25 equals x squared. So that means 6.25 equals x squared. So we need the square root of 6.25, which is going to be about 2.2, 2.3. Actually, a little more than that. Maybe 2.5. Anyway, let's do it on the calculator rather than just guessing. 6.25. And let's take the square root of that. 2.5 exactly. Oh, how do you like that? Okay. So x is 2.5. Okay. So that means the diameter of this circle is 2.5, which means the radius of the circle is 1.25. And what do they want? What they want is the radius. They want is how far the well is from each home. Now, the distance of the well from each home has to, by definition, be the radius of the circle, so your answer is 1.25 miles. The next chapter, Chapter 8, is about coordinate geometry. Coordinate geometry essentially means graphing. You start every problem of coordinate geometry with a graph. Now, a graph has to be on graph paper, something like this, with lots of different boxes. This graph doesn't appear to be perfectly evenly spaced, but it's close enough. Anyway, so the point is you've got an x-axis, which is the horizontal axis, and you've got the y-axis, which is the vertical axis, and you've got these arrows, which indicate that these really technically go on forever. Any point on this graph is listed as what is called an ordered pair. Let's say a point, for example, we'll put it at a random place. We'll put it, let's say, over here. Now, the way to figure out where this point is to simply count where it is on the x-axis and where it is on the y-axis. To this side is the positive of x, and to this side is the negative of x. This is the positive side of y. This is the negative side of y. This point, for example, is 1, 2, 3, 4 on the x-axis, and 1, 2 up. So this point is 4, 2. This point, for example, would be negative 1, 2, 3, 4 on the x-axis, negative 1, 2, 3, 4, 5 on the y-axis, so it's negative 4, 5. Generally speaking, this quadrant is going to be both positive x and positive y. This quadrant is negative x and positive y. This quadrant is positive x and negative y. And this quadrant is negative x and negative y. Okay, and of course you could also have shapes that are formed by different points. For example, this shape would actually be a looks like a parallelogram. If we connect the dots, I think we're going to have a parallelogram over here. So, actually, yeah, okay. Whoops. And figuring out dimensions and figuring out angles and figuring out lengths and things like that work the same way on a graph as you would on a regular piece of paper. So, for example, we can count the distances over here: 1, 2, 3, 4, 5, 6. As long as something is a straight line, you can count distances. This, of course, is also going to be 6 because it's opposite sides of a parallelogram. The question is, what happens if you have points that are not on the same line? You have one point over here and one point over here. How can you calculate these distances? Well, the answer is that you can calculate it using the distance formula. The distance formula is the square root of the change in x squared plus the change in y squared. This triangle means delta, which is Greek for delta, which in math means the change in. Now, this is actually just a derivation of the Pythagorean theorem. I didn't in another section I referenced it but didn't explain it. Now I'll explain it. No inherent reason why not to explain it. You don't necessarily have to remember why it's a derivation of the Pythagorean theorem, but why not? It can help. Let's say we were looking from here to here. Well, let's draw a different triangle, and let's draw a right triangle. Whoops. All right, let me make this a line. Let's draw a triangle from here and here. I'm just explaining why this works. Now, this point over here, what's this point? This point is negative 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this point is actually negative 5, 5. This point over here is 1, 2, 1, 2, 3. So it's 2, negative 3. We want to find the distance between them. If you were to draw this green line over here, this green right triangle over here, this of course would be a right triangle. This direction would be 1, 2, 3, 4, 5, 6, 7. This is if you notice, is the change in, this distance would be the change in x. This is the amount of slots it goes to the right. The height, on the other hand, of course, is the change in y. This is how high it goes, how high the shape goes. Now, the Pythagorean theorem in general is a squared plus b squared equals c squared. Now you don't know what this is, so we'll call this d because it's the distance of this line, the one that we're getting, the maroon one that we're trying to get. So in this case, a squared is, let's say, this line, so it's the change in x squared. This line, the vertical one, is the change in y squared equals, well, d squared, because that's the hypotenuse. Now, if you want to get d by itself, you can take the square root of each one. So you've got d equals the square root of the change in x squared plus the change in y squared. That's just the reason why the distance formula works. That's the derivation of the distance formula. But let's apply it over here. Let's eliminate all the stuff that we just wrote, and we will actually apply it as it applies here. So let's apply the distance formula into our case. Now we don't know. Oh, our points are -5. Their points were what? The points were -5 and -5 and 2 and -3. So if we apply the distance formula here, we've got distance equals, let me put it inside the box that you can see, distance equals the change in x. Now the change in x is, let's say, this x minus that x, 2 minus -5, which is 7, because minus -5 is plus, so it's 7 squared, plus -3 minus -5, in other words, -3 plus 5, which is 2, plus 2 squared. So our distance equals square root of 49 plus 4, which is the same thing as the square root of 53. Now, square root of 53 is about 7.2 or so, something like that. We can figure it out. We can put this over here. We can round it off by saying the square root of 53, which is 7.28. Okay, so we're going to say the distance is 7.28. So that means this side would be 7.28, and of course, since it's a parallelogram, this side would also be 7.28. If you wanted to figure out the area of the parallelogram, you would just do 6 times 7.28. If you wanted to figure out the diagonals and all that other stuff, you could use all the rules that would apply regarding the parallelogram. So that's the distance formula. That's how to find out the distinction between two, or the distance between 2 points on a graph. The next rule is the rule of collinearity. In other words, the question really is whether a point is on a line between one point and another. You've got one point over here, you've got another point over here. You can, of course, draw a straight line between any 2 points. If I wanted to draw a straight line between this point, I'd simply draw a straight line, and of course you can draw a straight line between any 2 points. No inherent reason why not. Well, what if you have a point and you want to know whether it's on this line? Now, one thing you can do, for example, you can just look at the line itself. For example, what are these 2 points? Let's write down what these 2 points are. This point is -1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. So one point is -7, -5. This point over here is 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. This point is 3 and 8. And I want to know, is this point -3, 0 on that line? Now, from the looks of my chart, from the looks of my graph, it looks like it is. You can see from the looks that it's right on the line. But let's say I wanted to figure out mathematically. And the way to figure that out is to find the distance between this point, let's say A and B, which is the one we're looking for, and B and see if they add up to AC. If B is on the line, then of course AB plus BC should equal AC, like any 2 lines. If it's on the line, this segment plus this segment should equal the entire thing. So let's apply the distance formula to figure it out. Let's figure out AB. And I'm going to do the distance formula pretty quickly. Distance formula is the square root of change in x plus the change in x squared plus the change in y squared. So what are we looking for? We're looking for this point. This point is point A, this point is point B, this point is point C. So -3 minus -7 is +4, so that's 4 squared. 0 minus -5 is +5, that's 5 squared. So d equals the square root of 16 plus 25, which is the square root of 41. Okay, so the distance is the square root of 41. Fine. Now let's look at the second one. Now let's look at segment BC. Segment BC is, the distance is, again, now we're looking at these 2 points, this point and this point. -3 minus 3 is -6 squared. Now -6 squared is +36. And the y component is 0 minus -8, which is +8, which is plus 64. So the distance equals the square root of 36 plus the square root of 64, which is the square root of 100, which equals 10. So these two segments, AB, we figured out was the square root of 41. BC we figured out was the square root of 10. Now let's figure out AC to see if that equals, see if it equals up to it. Okay, well, let's figure this out. So between A and C, distance again, square root of change in x plus squared plus change in y squared. 3 minus -7 is +7, so that's 10 squared. That's 100. Plus 8 minus -5, that's 8 plus 5, 13. And 13 plus, so 13 squared is 169. So d equals the square root of 269. So let's see if these two distances are the same. Here we've got the square root of 41 plus 10. Well, okay, let's get out our calculator. Obviously, we're going to have to round it off, but we can see if it's roughly the same. So let's take the square root of 41. 6.4. We're going to round it off to 6.4. And so plus 10, 6.4 plus 10 is approximately 16.4. What is the square root of 269? To see if that's also 16.4. 269 square root 16.4. There we go. Okay, so both, looks like they both, at least when you're rounding it off, they both have the same distance. The distance from here to here plus here to here is 16.4, and the distance from here to here is 16.4, which means B is properly on the line. What if I want to know the midpoint between 2 points? Well, the midpoint between the 2 points is, of course, the middle of the line that connects them. If it is a straight line like this, right on a line, well, then it's very easy. Then you can just count. The total thing is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that means 5.5. The midpoint would be right in the middle, in the 5.5 mark. So you just go 1, 2, 3, 4, 5, and then the midpoint would be somewhere right around there. Okay, what if they're not, however? What if the points are, one point is over here and one point is over here, and I want the midpoint of this line segment. Line segment starts here and goes here. How do I figure out the midpoint? Well, the answer is just take the average of the x value and the average of the y value. First, let's figure out the point where it is. 1, 2, 3, 4, 5. -5. 1, 2, 3, 4. So it's -5, -4. And this one is 1. 1, 2, 3, 4, 5. And this is 1, 5. Well, let's figure out the average of the x value and the average of the y value in order to figure out the midpoint. Well, the average, again, the way to get the average, just add them together and divide by 2. -5 plus 1 is -4 divided by 2, which is -2. And on this side, negative 4 plus 5 is 1 divided by 2, which is a half, or 0.5. So the midpoint is negative 2 and 0.5, which is right there. Obviously, the midpoint has to be on the line, and again, looking at it with the naked eye, it seems pretty apparent that the green mark is in fact at the midpoint of this segment. Next, let's look at the concept of slope. We've got a line that starts over here. Whoops. Let's get our graph back. There we go. We've got a line that starts over here and ends over here. So, what is the slope of this line? The slope means how fast does it rise as it's going from left to right, or how far does it fall as it goes from left to right. So a negative slope would go downwards. This would be a positive slope. I'll also draw a negative slope, and we'll figure them both out. This would be a positive. The one on the right would be a positive slope. This would be an example of a negative slope. Let's figure out the slope for both. Now, the way to figure out the slope for both is a very simple and straightforward formula. The slope, which is known as m, for some reason, just called the slope, is the change in y divided by the change in x. How much did the y change, and how much did the x change? Let's figure out this slope first. Well, you can really pick any 2 points on the line in order to figure out the slope. Using any 2 points, you'll get the same answer. Let's pick the beginning and the end. The beginning is 2, 2. And the end is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7. Okay, and the end is 12 and 7. So just figure out the change in y divided by the change in x. The change in y, just take one side, one y value minus the other y value. It makes no difference which one you use. You could use 2 minus 7 or 7 minus 2 as long as you're consistent about it. If you're going to use 7 minus 2, then you also have to use 12 minus 2. If you're going to use 2 minus 7, you have to use 2 minus 12. Either way, you're going to get the same answer in the long run. 7 minus 2 is 5, and 12 minus 2 is 10. Which is a half, or 0.5. So the slope of this line is 0.5, 1 over 2. That really means that it goes up a half for every one it goes over. Up a half, 1 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 over, etc., for the entire line. And this line could stretch infinitely in this direction or infinitely in that direction. And as long as it stays a line, the slope will be the same. Now let's figure out the red one. You'll see why this is going to be a negative slope. The 2 points on this one will say, what's this point? This point is negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So this point is negative 10, negative 8. Let me just count that again. Yeah. And this point is 0. It's on the y-axis, so the x value is 0, 0, 3. Let's subtract one from the other again. Makes no difference which one you use. So let's say the bottom minus the top. 3 minus negative 8 is... I'm sorry, this was a mistake. This of course was positive 8. I just realized I made a mistake before. This was positive 8, not negative 8. So 3 minus 8 is negative 5. So the negative 5 is going to be on top. And on the bottom is going to be 0 minus negative 10, which is positive 10. So this is actually also going to be 0.5, but it's going to be negative 0.5. It's really the exact opposite slope of this. For every 1 over a half down, 1 over a half down, 1 over a half down, 1 over a half down. Just to give you an example of a little bit of a steeper slope, let's draw something like this. Well, let's figure out the slope of the orange line. Okay. What's the points in the orange line? Negative 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Again, 1, 2, 3, 4, 5, 6, 7. Yeah, okay. So it's -7, -4. And this point over here is -1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's -3 and +9. So what's the slope? Well, let's see. 9 minus -4 is the change in y. That's 9 plus 4, which is 13, divided by -3 minus -7, which is -3 plus 7, which is 4. So the slope is 13/4, which is the same as 3.25. In other words, 3 1/4 up, 1 over. 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 That's how to figure out slope. Two important rules regarding slopes, and that is that if two lines have the same slope, they are parallel, and if two lines have slopes that are negative reciprocals, they are perpendicular. For example, we've got two parallel lines drawn over here. We'll call this line A and this line B. Let's figure out the slopes of both lines, and you'll see that they're the same. In fact, they look parallel. Slope A, let's take this point and this point. This point is 1, 2, 1, 2, 3. So it's got 2, 3. And this point up here is 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's figure out the slope of this. The slope is the change in y, 9 minus 3, which is 6. 4 minus 2 is 2. 6 over 2, which is 3. Now let's figure out the slope of line B. Well, line B, 1, 2, 3, 4, 5, 1, 2. So it's got a 5 and -2 point. And then we can pick this end point again. We can pick any point at which it hits. But let's try the end one. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this point is 9, 10. Okay, again, the slope is the change in y divided by the change in x. 10 minus -2 is 10 plus 2, which is 12. 9 minus 5 is 4. And 12 divided by 4 is 3. So notice these two lines are parallel to each other, and therefore they have the same slope. Or really, I should say they have the same slope, and therefore they're parallel to each other. Let's draw another line into the equation over here. And I'm going to take this green line, and I'm going to start it at this point. Oops. I'm going to start it at this point, and I'm going to draw a line that looks something like this. Okay. Now, what is the slope of this line? Let's figure it out. Let's take 2 points on it. Let's take this endpoint, which is at 1, 2, 3, 4, 5, 6, 1. Okay, so that's point 6, 1. Let's take a different point. Let's take this one all the way at the end over here. 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and -2. Okay, let's figure out the slope. Again, the slope is the change in y divided by the change in x. So the slope is -2 minus 1, which is -3, divided by 15 minus 6, which is 9. So the slope is -1/3. Now, the slope of A and B, if you'll recall, the slope of B, the slope of B, of line B, was 3. And M and the slope of the green line was negative 1/3. Those are what are called negative reciprocals. Negative, obviously you know what negative means. You just flip around. One is positive and one is negative. And a reciprocal means you flip over the fraction. 3, of course, is the same as 3 over 1, which is the reciprocal of 1 over 3. Because these two lines, the slopes are negative reciprocals of each other, that inherently means that this is perpendicular, this is a right angle, this is a 90-degree angle. Of course, if you have a coordinate plane with a quadrilateral on it or an angle on it, this could be an important way to prove that it's a rectangle, that it's a square, or whatever you need, a right triangle, whatever you need a right angle for. The way you do that, if you have a shape and you want to prove that there's a right angle, you got to prove that the slopes are negative reciprocals of each other. Just to give you one, okay. Two special types of slopes that I want to quickly mention. A flat slope is what is called a zero slope. And the reason for that is very simple. It's not going up and not going down, just kind of going flat. If you notice, the change in y is always going to be 0 if it's flat. You know, the slope is the change in y divided by the change in x. Well, a flat line, the y isn't changing. The y is staying the same, which means it's going to be 0 over something, and anything, and 0 divided by anything is 0. What about the opposite? What about this? What about something that goes straight up and down? Well, it doesn't really have a slope because it's not moving right or left at all. It's not really a zero slope because you can't say that it's not changing. This is what is called, let me write down here that this is a zero slope. This thing over here is what is called a no slope. Watch this. It's a change in y divided by the change in x. Well, y is changing, but what's the change in x? X is not changing. X is always staying the same. So the denominator is 0. Now, where the denominator is 0, the fraction is undefined. So there's none. There just isn't any. Next, let's go into writing an equation of a line. Writing the equation of a line has to have the y value and the x value have to be variable, have to move from place to place. For example, let's take a line something like this. Now this is, of course, a segment, but understanding that lines can go infinite in either direction. How do you write this equation? How would you establish to write a relationship between the x and y value on this line? And the answer is it has to be written into a form where you have y equals something, a number, a constant, times x plus another constant. In graphing, this constant, this first constant, is called m, we'll see why in a minute, times whatever x is, plus b. And in this form, m is the slope, and b is the y-intercept, where it intercepts the y-axis. Okay, so the way an equation looks, let's just look at the way this equation would look. Now this equation, I can see right away that the slope is 1. I don't even have to figure it out, because I can see it's going 1 up, 1 over, 1 up, 1 over, 1 up, 1 over. So this would actually be y equals 1x, or just plain x, plus b is where it crosses the y-axis. And you can see it crosses the y-axis at 1, 2, 3, 4. So the equation of this line would be y equals x plus 4. What if you get the equation first? How do you actually graph it? Let's say we've got an equation like this. We've got an equation is y equals 2x minus 2. First of all, right away we knew, is this in y equals mx plus b form? The answer is yes. It's basically a an equation that has a y equals something x and a constant. You have it in proper form. So we know right away that the slope of this line is going to be 2, and the y-intercept is going to be negative 2. How would we figure out where to put the points? Well, the way I do it, the simplest way I think, create a little chart. Put an x on one side, the y on the other side. In the middle, put what y is equal to. In this case, y is equal to 2x minus 2. Pick any three random values for x. Makes no difference what you pick. I'm going to pick 0, 1, 2. And figure out, based on this x value, what y is going to be. Substitute this number for whatever x is. So in this case, it's 2 times 0 minus 2, which is negative 2. If we then substitute the 1 for the x, we've got 2 minus 2, which is 0. If we then substitute 2 for the x, so we've got 2 times 2, which is 4 minus 2, which is 2. Now we've got 3 points. We've got 0, negative 2, which is right here. We've got 1, 0, which is here. And we've got 2, 2, which is here. If we then go ahead and draw a line that goes through all 3 points, we now have this line. Of course, it goes in all directions, but you can see right away that it's accurate because it has a 2 slope, up 1, up 2, 1 over, up 2, 1 over, up 2, 1 over, up 2, 1 over, and you can see that its y-intercept is correct, which is negative 2. If you don't get the equation in that form, if you get the equation in some other form, you get the equation, let's say, 2y plus 6x equals 10, well, then you have to solve for y. You got to get y all by itself. And the way to get y all by itself is to take everything off of that side of the equation. So we can get the 6x away just by using simple algebra. So I'll say 2y, and I'll use the x term first because that's the appropriate form. Negative 6x plus 10. The 10 stayed where it is. Now I still don't have y by itself because I've got a coefficient. I've got a 2 here. How do I get rid of the 2? Divide by 2, like you would in any other algebraic equation. Divide by 2 here, divide by 2 here. So you've got y equals negative 6 divided by 2, which is negative 3x, plus 10 divided by 2, which is 5. Now we've got it in y equals mx plus b form. Now we can make our little chart, and we can graph our point. Okay, we got negative 3x plus 5. Again, for 0, I'll pick 0, 1, 2. Negative 3 times 0 plus 5 is 5. Negative 3 times 1 plus 5 is 2. And negative 3 times 2 plus 5 is negative 6 plus 5, which is negative 1. So we've got 3 points. 0, 5, 0, 1, 2, 3, 4, 5. We've got 1, 2, which is here. We've got 2, negative 1, which is here. Let us draw our line. And there we go. Let's do a complicated example that will bring all of these together, all the things that we've learned in this together. Let's say you're given this and asked what are the four. What shape do these 4 lines form together? So let's graph each one. Let's graph y equals 2x minus 5. Let's do the first one. We'll call this 1. We'll do it in orange. So for y equals 2x minus 5, let's do the x and y chart as usual. Let's do the 0, 1, 2. So it's 2x plus 5. That's 2 times 0 plus 5, which is 5. 2 times 1 plus 5, which is 7. 2 times 2 plus 5, which is 9. So this we've got 0, 5, 1, 2, 3, 4, 5, 1, 7, and 2, 9. Whoops, that's 2, 8. Let's draw 2, 9. So let's get a line. Let's get a nice orange line that goes through here. Okay, I think that's about right. Let's do our second one in red. Y equals 2x minus 7. Again, we'll try the x and y. Okay, 2x minus 7. Again, we'll try 0, 1, 2. 0 minus 7 is negative 7. 2 minus 7 is negative 5. And 4 minus 7 is negative 3. So we've got 0, negative 1, 2, 3, 4, 5, 6, 7. 1, negative 5. And 2, negative 3. Okay. Now let's do a blue line for our third one. Y equals negative a half x plus 3. Negative 1/2 x plus 3. Again, let's try 0, 1, 2. This, of course, is 0 plus 3 is 3. 1 times negative a half is negative a half plus 3, which is 2.5. And then negative a half times 2 is negative 1 plus 3, which is 2. So we've got 0, 3. We've got 1, 2.5. And we've got 2, 2. And here I'm going to actually have to draw the line twice. I'll draw it once from this side, and I'll draw it once from this side in order to make sure that it crisscrosses properly. Okay. And finally, our last line. What color should we pick? Let's pick purple for this one. Y equals negative a half x minus 4. Okay. Negative 1/2 x minus 4. So x, again, 0, 1, 2. 0 minus 4 is negative 4. Negative a half minus 4 is negative 4.5, so negative 4.5. And then negative 1 minus 4 is negative 5. These go fairly quickly. 1, 2, 3, 4. And then 1, negative 4.5. And 1 and 2, negative 5. So now let's draw our line here. Our line starts here, and our line should go something like this. So we want to know, what is the shape in the middle? This thing over here. Oh, never mind. This is gonna make me shade. All right, let's shade them all in. Well, anyway, this whole thing. Whatever. Anyway, you get the point. Okay, this whole thing in the middle over here. Now, this should be a parallelogram because opposite angles are equal. I didn't draw this very well, but the point is opposite angles are equal. I'm sorry. What did we prove? We proved that it should actually be a rectangle. These are negative reciprocals of each other, so these lines should all be. I mean, just we don't even have to have graphed it. Just looking at the fact that the slopes are negative reciprocals of each other, the lines have to be perpendicular. So this is actually a rectangle. If we used the distance formula, we would be able to figure out the distance between here and here, and to prove that they're the opposite of each other. The last unit is about transformations, geometric transformations. Now, there are a whole bunch of different types of transformations, and I'm going to go through them one at a time. So let's first go through the first one, and the first one is a rotation. A rotation, let's take an example over here. Let's take a ABC triangle. Same thing is true with other shapes, of course. Rotation, you can flip it 90 degrees to the right, 90 degrees to the left. A rotation to 90 degrees, let's say 90 degrees to the right, which paint will actually do for you, it just kind of turns on its side. Same thing is true with a rectangle. If I have a rectangle that looks something like this, and I rotate it, this time let's rotate it to the left, it also kind of flips on its side. A triangle that's rotated 180 degrees, which means it's totally flipped over, doesn't change at all. It moved a little bit because of my box, but the truth is that this triangle is exactly on the same spot. If we would literally have a perfect box around it, if I could make a perfect box around it, which I'm going to try as much as possible, if I rotate this a full 180 degrees, I'm flipping over, you're not going to see any change whatsoever. We saw a tiny little change because of my inexactitude. And the same thing is true, by the way, if it's bisected. Watch what happens here. If I flip it 180 degrees, again, it's not going to actually do anything. You see, it really didn't do very much. Anyway, but this is really a matter of logic as to what's going to happen. Sometimes you're going to see questions, if something is rotated, does it change? Well, you just got to envision it being rotated. You can even pick up the piece of paper and flip it around halfway and see if it's changed. It's really kind of a matter of logic. Another thing that can be done is it can be reflected. A reflection can be in a line or it can be in a point. A reflection in a line means you kind of use the line as a mirror. In this kind of a line, this is just kind of flip over the line. The way we would illustrate that is by we can copy it and we can flip it. It's going to be upside down. We can flip vertical. It's going to look something like that. Now you can see right away why this works, because imagine the red line is a mirror, and this just kind of flips over the mirror and looks like that. If this was A over here, of course, and this was B, and this was C, then we would call this A prime, which is like the new A, and this C prime, and this B prime. Notice how they flipped directions, because the whole thing flipped over. What was over here flipped all the way over here, this flipped over to here, this flipped over to here. Next thing we can do is we can rotate it in a point. We can rotate this whole thing in this red point over here, which means everything gets reversed. The entire triangle, each point individually gets reversed. This B is going to go through the triangle and come out the same distance on the other side. B is going to come out around over here, C is going to come out around over here, and A is going to come out around over there. The way we do that, the way we illustrate that, is simply by taking the shape, putting it on the other side, and flipping it 180 degrees. Rotating it, 180 degrees. Something like that. Well, this is not exactly... Okay. This would be A prime, this would be B prime, and this would be C prime. And if this red line were actually in a proper point of rotation, and I'm going to try to draw a better one, would be probably somewhere around here. This would mean that this line would go through the line to A prime, and the distance of here would be the same as here. And then the same thing is true for the other lines. C would go through the middle to C prime, and again, the distance between C and the dot would be the same as the distance between the dot and the new C, and B would go all the way as well. The distance from B to the dot would be the same as the distance from the dot to B. That is a point rotation. For the next two that we're going to do, and really the last two as well, we're going to do translations and dilations. Translations simply means moving the shape over, moving everything over by a certain amount, whereas a dilation means changing the size. Let's take an example. Let's use a triangle over here. Let's say we had this triangle, and we put it over here, and we wanted to translate it. Let's say we wanted to put it in a translation of 8 and -3, which means the x, we want to change all the x values by 8, and we want to change all the y values by -3. So we'll call this, again, ABC. And the way we're going to do this is we're simply going to we're going to keep the dimensions the same. So let's count the height and the base. The height is 1, 2, 3, 4, 5, 6, and the base is 1, 2, 3, 4, 5. So we're going to keep those the same, but let's move the whole thing over 8 and down 3. X is going to be positive 8, so that's 1, 2, 3, 4, 5, 6, 7, 8. And y is negative 3, 1, 2, 3. And we're going to do the same thing except 6 down and 5 over, which is the same dimension as the previous example. So this new set over here is going to be A prime, B prime, C prime. Basically, it's the same as ABC. It's congruent to ABC. It's all the sides are equal to each other. The corresponding sides are equal. The corresponding angles are equal. Of course, these are both right triangles over here, just because this happens to be the way I drew them. But so this is the same exact triangle, but it is in a translation of positive 8 for the x value and negative 3 for the y value. And finally, let us look at a dilation. I'm going to take something that's relatively small and make it a little bit bigger. Dilation means you're making it bigger, or you could even make it smaller. Either one would be a dilation. But we're going to make let's take a small triangle to start with to make it easier to dilate. Let's say we've got a triangle here, and this triangle we'll call ABC as usual. We'll call A, B, C. And let's say we want to dilate it by multiplying it by 1, 2, 3, 4, 5, 6. Okay, so multiplying it by 2. Let's say a dilation of 2, which means all the sides are going to be twice as big. Let's get the points. We'll keep it in A. We'll start it with A. Let's put the C down here. You'll see why. We'll use A as the center of the dilation. In other words, A is going to stay the same, and the others are going to grow. How high was this? This is 1, 2, 3, 4, 5, 6, 7. The height was 7, so let's make the new one another 7 high. 1, 2, 3, 4, 5, 6, 7. So we'll put this as 7, and this is 1, 2, 3, 4. So we'll do another 4. 1, 2, 3, 4. The new triangle, in other words, the original one dilated, we're going to start down here. Let's put this up here, and extend this out here, and put the hypotenuse, since this is a right triangle. We'll put this all the way down here. So now we'll name the new ones. Well, this A, and this is also A prime, by the way, since this is the center. This is both A and A prime. Up here is B prime, and up here is C prime. Now, of course, this was doubled. All the sides were doubled, which means that if this side was what, 5? So the whole side altogether was 10. This side was 7, and the whole side altogether was 14. The hypotenuses are also going to be doubled. If we use the Pythagorean theorem, we should see why. This is a squared plus c squared, a squared plus b squared equals c squared. 7 squared plus 5 squared equals x squared. 49 plus 25 equals x squared. That's 74 equals x squared. So this is the square root of 74. And the long one, b prime, c prime, well, again, let's use the Pythagorean theorem again. That's a squared plus b squared equals c squared. 10 squared plus 14 squared equals c squared. 10 squared is 100. 14 squared is 196. Equals c squared. 100 plus 196 is 296. So 296 equals c. So this is the square root of 296. It doesn't look like it's double, but it is. This is the square root of 74. This is the square root of 296. If you want me to show you that it's double, let's figure it out. Square root of 74 is 8.6, approximately 8.6. It's an irrational number, but we're rounding it off to 8.6. And the square root of 296 is 17.2, which is double 8.6. So this is double this. What about the area, by the way? The area is not going to be doubled. The area is actually going to be quadrupled. Because in one dimension they're doubled, so in two dimensions it's going to be quadrupled. Just like if in one dimension it were multiplied by 3, in two dimensions it would multiply by 9. If we figured out the area, for example, the area of the small triangle, the area of ABC is, remember, base times height over 2. So the base is 5, the height is 7 divided by 2. 7 times 5 is 35. And divided by 2 is 17.5. That's the area of the small triangle. The area of the big triangle is, again, base times height over 2. The base is 14. The height is 10 divided by 2. 140 divided by 2 is 75. Now, so this, of course, is the 75 is exactly 4 times the 17.5. Of course, notice that these two triangles are similar to each other. ABC is similar to A prime, B prime, C prime. This, of course, is an angle for both. These two lines are parallel, and therefore this angle is equal to this angle. They're consecutive. This angle is equal to this angle. They're also consecutive. So these two are similar. All the sides are in proportion with each other.